I think Suzanne is still recording. In
Yeah.
my view, it shows it's recording. Suzanne, can you confirm if you're still recording?
I am recording.
Okay.
Right, so I'm going to follow the same pattern as Hannah in subdividing the contribution between various members of our group. So I'm not going to rehearse the aims of Pillar 3 or anything, because in view of the time, I did give that, did explain that at the last meeting we had. So what I'm going to do is just first introduce you to the cast. So members of P3 are Ram, whose main interest is in robotics and physics-informed machine learning, decision-making under uncertainty. Myself, I'm interested in automated reasoning and representational repair. Alex Laskaridis, who's another co-I, interested in natural language processing and interactive task learning, and that's going to be the focus of her contribution to our work. Andrew Ireland, interested in automated reasoning and formal methods and software engineering, and Alice Miller, trying to get rid of this thing that's obscuring the picture, interested in formal verification, especially model checking and symmetry reduction. And then other members are Paul Jackson, interested in formal specification and verification and automated reasoning. Ajitha Rajan, software engineering, automated testing for models and code. Matthias Appelgren, one of our PDRAs, interested in natural language processing and also interactive task learning. And another one, Yu-Hai Lin, theorem proving and automated reasoning. And lastly, Craig Innes, interested in robotics and planning and specification. So I'm going to now hand over to Alex to talk about how we were planning to work on incident reports. However, that work, as she'll explain, is currently halted for reasons of illness. But Alex, do you want to start talking about this slide?
Yeah, sure. Can everyone hear me? Can you hear me?
Yes.
Good, great. Yeah, actually the halting of this plan is not purely because of illness, but also because of serendipity. So when Craig joined the group, he already had a system in place that I'm going to talk about shortly. And because he's employed until December, we wanted to use his time for him and Matthias to work together to do the interaction stuff that I'm going to talk about shortly. So there was an intellectual reason for delaying this particular work package, which we made before the PDRA. Matthias got ill, but then he then got ill. So in fact, both pieces of work are delayed because his illness is an ongoing situation. Anyway, let me explain what we're going to do. Incident reports are, what we've done is we've collected incident logs on drones, and we've examined them sort of, they're a mixture of maps, pictures, free text. There's often summaries, which are then qualified with much more detailed reports. They have a structure for sure, but really, technically, this stuff is considered unstructured data. And our aim is to use and to explore the extent to which existing natural language processing technology is able to extract from this unstructured data structured information, and in particular, structured information about who did what to whom and when. So we want a temporal timeline. A lot of the information in these reports, we've read a lot of them, is implicit. In fact, quite often the really critical thing is implicit. So for example, you'll have a report about a drone crashing to the ground and it says, and the parachute was opened suddenly, blah, blah, blah. And it doesn't say it was a bad thing, that the parachute opening was an unexpected thing. And in fact, it's the cause of the accident. And that's not said either. So it's quite important to at least get in a structured sense information about time from these reports, and the information about time itself is often implicit as well. So we're going to look at unsupervised learning methods and leverage an existing body of work on unsupervised learning methods for extracting this information, test the extent to which it works on this data on which it's untested, and through error analysis, hopefully improve it and tailor it to this data. Next slide, please, Alan. The other goal or role that natural language processing is going to play in the task governance node is in enabling software developers and regulators to interact with a simulation system. So what you see here on the, I don't know my left from my right, on the right, if you could move your cursor, Alan, as I talk, is a sort of formal language which Craig has developed to interface to a robotic simulation system, a picture of which is there in the bottom center. So this formal language provides both a specification of the environment in which the task is going to take place and task specifications. And from this, you can sample specific environments in which the robot will attempt to perform the task as it's specified in this formal representation of the task specification. And because you can randomly sample specific environments, you can test the extent to which the robot succeeds or fails in various renditions of that environment specification, and the extent to which it fails, if it fails. But we don't want people, as in humans, having to learn this formal language. And so what we want to develop is a natural language wrapper, essentially, around this. So it's a natural language understanding problem. And it is one that's well understood in the realm of semantic parsing, which is a particular subfield of natural language processing that's very well developed these days. But typically in natural language semantic parsing, the way the process is done is you have a huge training corpus of natural language utterances paired with their formal semantic representation that supports automated inference, or in our case, generation of specific simulation environments. And you train on that using whatever your favorite machine learning method is. We don't have that luxury. We don't have that training corpus. So what we want to do, and where the innovative technology will be developed by a combination of me, Matthias, and Craig, is instead of having a batch learning approach using these vast corpus of natural language formal semantic representation pairs, we are going to leverage evidence from the interaction to improve existing semantic parsing. So the way we're going to do this is by developing, first of all, a seed grammar that associates natural language utterances that are within the coverage of that grammar with semantic representations that are derived from the linguistic form of that utterance. So that's what's labeled sentential parsing here. Now, of course, we can't control what humans say, and they're going to say things that are outside the grammar. When that happens, it's going to trigger a dialogue strategy between the human and the system. So the system will ask for words that are outside coverage, is this word like this word? And it will also use word embeddings, which we can get off the shelf to handle a lack of lexical coverage. Where it's a lack of construction coverage, the system will trigger questions, which the human will then answer, about paraphrases, which are within the purview of within the coverage of the grammar. So essentially what we'll be doing is enabling the system to ask intelligent questions by exploiting shallow language processing and semantic representations that go with that shallow processing. And then through the question and answer sort of thing that gets triggered between the human user and the system will learn how to glue together the semantic shallow representations into a deep representation, and so generate new rules within the grammar so that the grammar's coverage extends through the course of the interaction. So I think that's all I want to say at this point in the interest of time.
Thanks, Alex. Before we move on, I just want to point out that this image here is generated by a simulation program called Carla, which I'll be saying more about this afternoon when we're talking about simulations. Okay, so next up is Andrew, who's working with UQuai and Craig and Alice on formal analysis and simulation. And here's that Carla system that I just mentioned. Andrew.
Hi, can everyone hear me?
Yep.
Okay, so this slide depicts the different perspectives that we're endeavoring to integrate in P3. Before I go into the details of the picture, I just wanted to highlight the motivations for this kind of integration. So we're looking to integrate formal methods with simulation, and these are complementary approaches. And the aim of doing this is that we'll get more comprehensive feedback early on our requirements, on our regulations as early as we can within the development process. And a key enabler as well that we're integrating here is the natural language processing that follows on from what Alex has just said. And I'll talk a little bit about that towards the end of this. So the focus here in the picture is on automotives. But that's really for pragmatic reasons. There's a lot of data out there for us to test our ideas out on. But ultimately, the ideas here could move into newer domains like reasoning about drones and the regulations around drones as they emerge. So at the top of the picture is governance and regulation, the generation of the constraints by which we are going to build our systems. And then below that is what's been termed here the natural world. So the HD maps are essentially a representation of the topology of transportation networks in an automotive setting. So that's really important, you know how things fit together in terms of the movement of vehicles on the highways. And also next to it is trajectory data, incident data, essentially data from the real world that will help drive simulations. Moving down to the abstract level, so the idea is that, well, we're exploring a number of different logics and the reasoning support therein to look at abstractly regulations, to formalize them first off and to analyze them for inconsistencies, and also to look at requirements that will feed into task specifications, which the requirements don't really figure in this slide, but they essentially feed into task specifications. So we're looking for inconsistencies, but we're also looking for abstract obstacles, things that will prevent certain requirements from being met, from being achieved. And then moving from the abstract world into the simulation world, that's been driven by the abstractions. We'll look at particular scenarios around task specifications. And this brings on into view here the Carla system that Alan has mentioned, and I think Alex mentioned with respect to Craig's work. So this box is really all about Craig's work with RAM, which is about, in a smart way, looking for simulations that will yield the most information about the robustness of the systems we're building. Okay, so just taking a step back from the abstract world, we're getting feedback early on, but also from the simulation testing world, we're getting information about corner cases and explanations therein. And crucially, the two NLP layers are in there, and these we see as vital as bridging the gap between the formal and the simulation back to the sort of world in which the language in which regulators and the language in which system engineers and requirements engineers speak. That will be crucial in bridging that gap. So I think that's all I wanted to say, Alan, about this.
Okay. Thanks very much. So next up is Alice Miller. Now, she's going to be talking. Why isn't this working? It seems these slides have got stuck. I'm going to unshare them and share them again. Right, good. Okay, that seemed to work. If in doubt with a computer system, shut it down and start it again. So Alice is going to talk about a number of projects she's been involved in, which were not funded under TAS directly, but are very relevant to TAS. And we have taken the view in P3 that we want to include other projects which are relevant and consider those as part of the project as essentially additional funding that will enable us to achieve our objectives. So Alice, you're going to start with this old work on published in 2020, yes?
Right, okay. Can everybody hear and see me?
Yes.
Okay, great. Yes, so the work on the far left-hand side was some work I did a couple of years ago, which involved the use of the model checker Prism in order to do a bit of model checking with a drone moving around in a lab. So this was some work with some engineers at Glasgow that we did. So basically, we just wanted to try and combine their actual physical UAVs and a simulation model and also a Prism model, just to see what we could do. And we did that in order to develop strategies for moving around and finding objects in order to be able to find them with as quick as possible. So that's that work on the left. So if you want to shoot down to the bottom left, Alan. So this is more recent work, and although it wasn't initially funded by the project, I did do the writing up while the project was running. So I did put an acknowledgement to the project on the paper. So I think the project can own this paper. So I went back to using the SPIN model checker. So those of you who don't know about model checking, SPIN is a non-probabilistic temporal logic model checker. And we were using SPIN. I was trying to get this business of combining simulation and model checking again, because we're now focusing on trying to connect the two things together. So I was using the simulation was via this Unity game engine. This was a master's student who was doing this, and we were extracting information from that to the model checker in order to plan safe overtaking maneuvers, and that was quite good fun. I mean, it had problems in the end because of just converting things into a C program took too much time, so we had to pause things as we were going along. But the actual model checking side of things was close to real time. And it showed as a proof of concept. So now moving down to the bottom middle, with Andrew Ireland, we have been involved in a project proposal as part of the NATEP scheme, and this is with DRISC. And we're still waiting a final decision on this project, but the basic idea is to embed Prism, so the probabilistic model checker, into the back end of their requirements engine, Caesar. And then moving around again to the right again, this is a pump priming project that I'm involved in, which is being led by Ina Omorinia, who's at Glasgow. And I'm not going to say too much about that because that's really his project. I'm just sort of a minor part of that project, but it's about consent verification anyway. And then finally, shooting up to the top right, this is an iCase award that I have with my student Douglas Fraser. And I think this, because we're looking at digital twins here, I think this does really mesh in very well with the project because it's all about simulation and formal verification and linking those two up. So I thought it was worthwhile putting this in here. And this is using he's currently using a different model checker, which is SpaceX, which is a hybrid model checker, which is a very efficient. It uses these things called flow pipes in order to overestimate state values, and it's much more efficient than normal hybrid model checkers, which are basically too inefficient to use in practice. So we're currently using that. So that's just a whistle-stop tour. I promised Alan I wouldn't spend more than a couple of minutes. So over to you, Alan.
Yeah, well done. Thank you very much, Alice. That's quite a tour de force. And lastly, but certainly not least, we're going to Ajitha Rajan, who is just got a Royal Society Industrial Fellowship working with Coldplay, and will be also doing the project she's going to talk about, which is very relevant to TAS. So over to you, Ajitha.
Thanks, Alan. So the project I'm going to briefly talk about, because I haven't really started working on it yet. It's only meant to start in March 2022. And this project is along with Codeplay Software, which is a company in Edinburgh. They develop compilers and acceleration technologies for deep learning algorithms. So the problem is that that we're going to focus on is that a lot of AI tasks in autonomous vehicles, so particularly focusing on perception tasks like object detection, lane detection, pedestrian detection, and semantic segmentation. So if you take any AI task, they run on very, very powerful hardware accelerators. And a lot of testing and safety checking for AI tasks that has been done has not really considered the hardware that they're running on. And often, you know, we might, when you simulate, you might use a certain GPU, but the chip that you finally deploy on might use a different GPU architecture or ASICs or FPGAs, whatever the hardware accelerator is. And what we found in past work is that the interaction between the hardware accelerator and AI task is important to keep in mind for safety checking, because the accelerator can give rise to memory access bugs, timing violations, API usage errors. So in fact, the paper that's shown below, which is a taxonomy of real faults in deep learning systems, found that one of the 5 main categories of real faults in perception tasks like object detection were because of GPUs and the misunderstanding behind how to use them and the parallelism related bugs that might occur. So this project really is to try and develop automated testing and formal verification techniques to check safety of AI tasks running on different hardware accelerators, and also trying to formally specify timing requirements for these perception tasks. So if you say that you want your object detection algorithm to complete within 2 microseconds, then you want to make sure that regardless of the hardware accelerator it's running on, the answer always comes back in 2 microseconds. So these are the types of things we are aiming to do. In addition to the Royal Society Industry Fellowship, this project is also supported by Data Lab studentship. So we're hoping to hire a PhD student as well to work on this project. That's all I have to say.
Thank you very much, Ajitha, and to all the co-presenters. You've proved that we can keep to time, and we've got even 5 minutes left for questions. So I see we've collected quite a lot in the chat. Let me stop sharing. Okay. How do you want to play this, Ram? I can pick these comments out of the chat, or we can ask people to.
I will leave it to you, but both are fine by me.
Okay, so yeah, I think the first one is probably from Stuart to Alex, and it's all about how will you know that a parachute deploying is unexpected? So Alex, you want to?
Yeah, so I think that's going to be a really challenging task and probably beyond the scope of this project. That's why I think that we need to see how far we can get, which is actually explicitly what this work package was designed to do. What we plan to do is use existing the existing work from Dan Roth's group. Dan Roth and his lab have trained, used unsupervised learning on a thing known as the gigaword corpus, which is like a massive corpus of natural language text, to estimate for each event the common sense knowledge about when it occurs and how long it takes. So it's essentially extracting real world knowledge, right? Now, that's an open domain thing because it's a gigaword corpus and it's all sorts of domains. So of course, you know, parachute opening is normal in some contexts and not in others. So we're not going to be able to handle that. But what we might be able to handle is estimating when an event took an unusual amount of time. And that's probably quite useful if you're trying to work out or search for things that went wrong. So what my hope is that the structured data we extract will help search for edge cases rather than actually tell you what caused what.
Okay, thank you. Peter has asked a question about the limitations of simulation in providing legally adequate justification. Maybe Andrew, would you like to answer that?
I'm not sure I'm particularly well qualified to answer that. It sounds like more like a legal.
Well, the reason I picked on you is that you're combining formal reasoning with simulation, so they're complementary. And maybe, you know, one argument would be that the formal reasoning is filling the gaps that the simulation can't provide, and that you know, if you can prove that you're, for instance, meeting various legal regulations in the formal reasoning, that might be the route to the legal side. I don't know.
Yeah, I mean,
that.
The integration is important because, as we know, the formal modeling is in one sense more complete, but it's very abstract, so it's incomplete. And the simulation, these massive simulations can go into much more detail, but you have to be much more prudent about what simulations you actually pursue. So you lose completeness on that side. But things that you learn in the simulation side may help you inform the formal model. And if the formal model is linked to your requirements, potentially the simulation will lead you back to omissions in your original requirements. But it doesn't give you any absolute guarantees. It's about improving, I think, the overall quality of the process.
Yeah, I just want to back up what Andrew's saying, that, you know, the simulation is not simply testing an existing formal specification. The idea in this paradigm is it's a two-way street, that the user who is observing these simulations and seeing where it goes right and where it goes wrong, actually through the natural language interface has an opportunity to change the task specification or to restrict the specification of the environments in which the task should take place. So the formal model will always be abstract, but through this interaction, this extended interaction will become more and more specific.
I think this is going to a combination of the things that you've just talked about. You talked about the parachute, for instance, in relation to this. So a lot of the adversarial situations that we've seen are looking at what I would call autoimmune responses from the system. So they look at what are your failure modes. I stimulate that failure mode, but there isn't a correct mode. Yeah, it's correct in one-off. It's not correct if I'm talking about everybody in the system shutting down in that way. Yeah, and those aspects there of it's indistinguishable. It's not a, yeah, are things. I think that's a really critical problem, and how you use formal models in relation to that is an area that is extremely interesting to explore. But I think the issue you have there is most attacks take place outside the model.
Yeah, so I should stress that the work on incident reports and the work on this interacting with a simulation system, they're not formally linked in this project, precisely for the reasons you say. It would be too hard to do. that's future work. It's beyond the scope of this project.
Ajitha, you wanted to come in on this.
Yes, just very quickly. I know we've run out of time. I just wanted to say that I agree that simulation is never going to be able to replace the infinite space of possibilities, but we do simulations because we need to resort to some feasible or tractable means of sampling the space. And often simulations are done to show that the model is working correctly. So the example you cited with the cyber physical system attack, that is usually sampling from invalid inputs, which, so that's the difference between security testing and correctness testing, is that here we try and sample from the valid input space to try and show correctness. But in the other hand, for security, you try and sample from the invalid input space, which is much larger and even in some sense a harder problem because simulation doesn't even cover that. So you're right, the problem exists, but it's not easy to come up with a solution that would still be tractable if we start looking at the infinite space.
Andrew, Stuart has a question here about how challenging do you see the process of formalization of regulations?
I think it's a spectrum. From the point of view of automotives and the kind of traffic regulations, that's kind of part of the standards. There's been a number of groups have worked on formalizing traffic regulations in different countries. So Craig and you have been looking at these, working with these. The similar, as you know, the similar rules of the airways for, when you can travel through an airway and what levels you should be occupying. And people have formalized these rules many years ago. So that's, they're in a sense, the low-hanging fruit. I was interested by, I think it was Jane Fenn from BA Systems gave us the talk quite recently. Ewan Denny was in that call as well from NASA. So they're very much looking at a goal-orientated approach to regulation. And that appeals to me. And it also points to some work that we've been looking at in P3 on a methodology called chaos, which is one of the few formal methods that's try to embrace the informal and the formal, but be driven by objectives and goals and refine these down, keeping a sense of consistency. So that would be my answer.
Thanks. Yeah. Looking at the remaining questions in the chat, it seems to me that most of them have been addressed in the conversation already. But if you think I'm wrong and want to come back, now's the time to shout. Okay, Ram, I think we're done.
Okay, perfect. I just put in a message saying